Hello.
Good evening, ma'am.
Jayanthi ma'am?
Can you hear me?
Yes, ma'am.
Okay.
Shall we start, ma'am?
Yes.
Good afternoon, one and all. Myself, Rajkumari Chilkuri, Assistant Professor. I would like to introduce about the eminent speaker for this session, Deep Learning for Medical Image Analysis in Disease Classification. Dr. Jayanthi Sivaswamy, working as professor in IIT Hyderabad. She has doctoral degree from Syracuse University. Her research interests includes the image processing, medical image analysis, and biological vision. She acted as chair and member for review for international conferences. She delivered many training programs at various national and international seminars. She has published many research papers in various national and international conferences and journals. She holds the excellent projects like retina image analysis, histopathological image analysis, brain image analysis, image reconstruction. It's my privilege to welcome you, ma'am.
Thank you.
Thank you, ma'am. Okay, I'm going, sir.
మీరు వీలుంటే కలిసి సార్తో వాటి అక్కడ నుంచి జాయిన్ అయ్యి ఓటర్ చెప్పండి.
Yeah, should I start?
Yes, ma'am.
Yes, ma'am.
Okay. Thank you for the invitation, especially to Dr. Padma Sai. She has been writing to me for several months. The planning is really great. She has sent emails well ahead of time. I wish I had planned well because there's a power cut here. I'm hoping the power will last for the duration of talk. So if I have to cut short, please bear with me. Let me share my screen. Can you see my screen?
Yes, ma'am.
Okay. So I slightly changed the title. The content will be as announced. So I work in the area of medical image analysis. So I'm going to be talking about that. So I will introduce first about the various imaging modalities that exist in the medical domain. Unlike computer vision, which uses primarily optical image, in medical imaging, we have very many modalities. Then I'll move on to, once you have the images, how you analyze them, and then how we can do machine learning to do the medical image analysis, and particularly deep learning. Deep learning, particularly, I will be looking at the context of computer-aided diagnosis, which is essentially how to help doctors with a pre-trained tool. And we'll close, hopefully, with a case study from my own group. So here is a look at many different types of images, some of which might be familiar to you. So these are all orthopedic images. So you can see, one second, let me get my. laser pointer. Yeah, so you can see some broken bones, skull, and so on and so forth. Now they all look, and this looks also something familiar to you. Hopefully it is familiar because this is your backbone or the uh, vertebra. Now there are differences between these images. So for instance, this is also the image of the backbone, but taken with an X-ray. And it's a 2D image, whereas this is a 3D image. I'm showing a 2D part of it, and this is an MRI, and you can see the difference. It captures soft tissue and so on, which the X-ray doesn't. Now CT is also X-ray based, but it is 3D, so it is a volume image. So these two are volume images, and this is a projection image, and which means 2D image. Moving on, so this is another image you must be familiar with because many families will share the happy news that somebody is going to be a mother, and then there is a scan taken and so on. So this is nothing but an ultrasound 2D of a fetus, which is still in the mother's womb. And this, on the other hand, is the more familiar image for us, which is the optical range of wavelengths that are used. And this is a 2D image of our retina in the eye. Finally, the last class of image that you should be aware of, but you probably are not familiar with because it is a bit rare, it is the nuclear imaging. So when you want to go for an understanding of what's wrong and if there is cancer and has the cancer spread, then you go for nuclear imaging. And this is a 3D image of the full body because we want to know if the cancer has spread. And you can see one view, and this is the side view and so on. So why do we have so many images? Well, we want to see at multiple scales and understand our body. So for instance, this is your mammogram, which is basically a picture of your breast. And this is at a scale where, you know, this size, this many pixels correspond to 5 mm in the actual scale, 5 mm of the tissue. And if they find something bad, as the arrow points out, then they take a biopsy, or in other words, they take a piece of tissue from the breast and put it under the microscope, and then you get a 2D image. Now, why are these color? Because they add chemicals, which means they stain it. And so the image on the slide can this much, it's at the same scale, 5 mm. But because it's a microscope, I can magnify it tremendously and see even at the 250 micron level or a micron level. Now you will see lots of markings. So this basically, this blue area has been blown up and you can see the details. And you can see different types of tissue here, which the pathologist studies and declares if things are good or bad. Now I can go to nanometer level also and take an image, and that is a different kind of microscope, and this is found in both academic institutions, mostly academic institutions. So this is what we call an electron microscope, and this is the coronavirus seen through the microscope, electron microscope. So if you look at the virus itself, it is 10,000 times smaller than the width of the human hair, but it will, when I blow it up, it looks like very, very real, and you see all sorts of structures, and that's because I'm looking at things at nanometer scale. So to summarize, medical images can be taken at a wide range of physical scale. So if this x-axis represents a physical scale, I can go from nanometers to macrometers. So we are, you know, our height and our body is at the macro level. So you see the body is imaged at the macro level. Then if you go to organs, you go to centimeter level. cellular level, intracellular, molecular, and so on. Now, typically the molecular intracellular level is more at the research level, and clinical, that means hospitals, deal with things which are tens of centimeters up to a meter. And that is the range at which we are dealing with in medical images. So if you look at how images are formed and why there are so many modalities, we can go to signal processing view. So basically there is a body to be imaged, you excite it, and the body responds to it, and you excite it with a particular wavelength source, such as X-ray, and then the body reacts to it, and then you sense. So X-ray will pass, and then on the other side, you do a sense, put an array of sensors or do measurements, and you can sometimes get the image directly. That's what happens in an X-ray. Whereas in an MR, you have to measure and do a lot of computation, and that is what we call as a reconstruction process, and then only you will get an image. So this is why if I change the excitation source, I get the image formation in a different way. So optical image is where this is my ambient light. This is the body. It reflects the ambient light, and there is a CCD array, and immediately I get an image. Whereas in ultrasound, I push in, I pump ultrasound, and then I get back some reflected waves, and I reconstruct it as an image. So this is the basic of how images are formed in medical domain. Now let's move to how do I process such images? So which means what is the role of medical image analysis? I'm going to give a very different view in terms of practically how is it used. When I compute something with the medical images, who does it help? So for instance, it can aid the obstetrician. So obstetrician is the one who sees a woman through her pregnancy and delivers a baby. So many times they want to know how healthy is the baby and what is the actual age of the, because many times women don't know exactly when the pregnancy started. So the gestational age is something of interest because they need to plan on when the delivery can happen. So for that, they do a measurement of the head. This is the head of the fetus. It might not look like that, but that is, so it's a bony skull is appearing as a white thing. And so you want to do an automatic measurement of the fetal head. And the measurement of interest is basically the circumference of the head. So then you calculate what is the circumference. So now you can see it's an ellipse. So I first detect it, then I fit an ellipse to it, and then calculate what is the total number of pixels lying on the ellipse, and that I convert to the millimeters. So this is one example. A second one is, let's say there's a neurosurgeon, and the neurosurgeon is trying to do a surgery on a patient's brain because they want to remove a tumor. So the question being asked is, how big is the tumor? And can I identify the key parts? So I have good news. So my power has come. I'm going to shift my location. Just a minute. So in this case also, you want to basically, this is a tumor region, and you want to automatically segment out and identify different parts of the tumor region. So what do? You take different modalities of MR because each modality gives good contrast signal to different parts of the tumor. So these are the three different modalities in MR. So you take all of them, so you process each one of them, and then you combine the results and show it on the original T1 MR image. So you combine the results and visualize. So visualize because these colors are all pseudo colors, they're really not colors. They are just basically gray values mapped to some color. So this is another example of how you can use image analysis to help a neurosurgeon. So let's look at one more example. So I already said that nuclear imaging is used for studying the spread of cancer. So an oncologist, how can we help the oncologist with image analysis? Well, typically this is the nuclear image that we take of the person who has cancer. So this is what we call as a functional image, meaning there is tissue, but is the tissue healthy or not? That is the question we are asking. Is it functioning normally or not? And that is what nuclear imaging will tell you. Whereas once I find something bad, I need to locate it. So something is bad here. So I need to precisely locate it, in which case I need a structural image. So just because I have a heart doesn't mean it is functioning properly. So similarly, lung cancer, this is a lung cancer case. So there's a lung and there is a cancerous piece here. So you are looking at the exact location of the lung and the boundary and so on. So for that, you need a structure image. So you combine the two and you do a fusion. So you have to automatically spatially align the MR and the PET image, then fuse the information from the two and do a pseudo coloring so that the oncologist can see at a glance where is the cancer, how big is it, and so on. And finally, once the cancer is established, we want to grade it or stage it, because usually cancer, they say stage 2, stage 3, and so on. So how do they grade? And for that, you have to go to the pathologist. They take a tissue sample and look at what sort of mitosis level are happening, and is it a metastatic stage, and so on. So for that, they take tissue samples. So these are 4 by 4, 16 samples, and you automatically detect the cells you want. And we can do this. You can see this is a very, very laborious task, and image analysis can help here also. And it can also count how many of them are there. And based on the count, they'll give a grade to the disease. And so once you have decided what stage you want to do a treatment planning, so how much radiation should be given? So chemotherapy means you are giving some chemical treatment, so in the form of tablets or solution. The other is you burn the tissue, which is bad, the tumor and so on. So that is through radiation. And how much radiation should be given such that the tumor dies, but the healthy tissue remains, is the key question. So the dose is calculated based on both MR and CT images. And as you all know, to take each image is very expensive and time consuming. And so the image analysis, now this is the latest advance in the last few years, that given an MRI, I can use machine learning to estimate the CT of the same patient to save cost and time. So this is the computed CT, not the actual CT. And this will save time and money for the patient. So this is another example where image analysis can help. So now I already said this is an example where machine learning played a role. So let's look at machine learning a little more closely. So traditionally machine learning typically starts with data, in our case medical image data, and extracts features from it and passes it on to a classifier to come up with a decision about the data. Now, these two stages do a divide and conquer strategy, as in, if I know very good set of features, I can extract them, and the classifier can be not a very discriminatory classifier. It will still go a good job because the feature space is such that the good and the classes are highly separable. But if I don't know very good discriminable features, then I will extract all sorts of features I can think of, but design a classifier which can do very fine decision boundary. And that is what I mean by either you have a very strong features extraction stage or a strong classifier. And you can do, this is in unsupervised learning case. Now, if you put a information about the ground truth on where the decision boundary should actually lie, we also call it annotation, and train it, then the classifier will learn in a supervised manner, and we call that as supervised learning. So we have two types of approaches to machine learning, supervised and unsupervised. This is a very basic classification I'm talking about. Now there is a huge paradigm shift in post-2000. So what is this paradigm shift? Let us look at it. So artificial neural networks were proposed in the 60s, which is 1960s, which is very, very long time ago. And these were very popular, and they were looked at to do machine learning and solve tasks in speech recognition, image analysis, and so on. But it hit a wall, so interest waned. There are a lot of limitations. The networks could not be built with a lot of depth, and training them was very difficult, and the performance hence was also bad. So the pattern recognition that they could do was not very impressive at all. So they moved to other kinds of machine learning. Then come post-2000, Jeffrey Hinton, who is considered as sort of the father figure for the Renaissance. He came up with a new version of the backpropagation algorithm and a training technique along with Bengio to improve the performance of artificial neural network. Now these two, the training technique, which allows you to do gradient descent based training, really meant that I could have a renaissance of artificial neural network, in the sense I could build deep neural network, and I can train them layer by layer so that the whole network learns complex representations. So the early stages of the network does basic stuff, edges, and then progressively as you move to deeper in the network, it learns more and more sophisticated features or complex representation. So this led to the paradigm shift that I'm talking about, and that is deep learning paradigm. And now we have what we are witnessing in the last at least 10 years is an explosive growth in this paradigm application in all sorts of areas, speech, text, speech, whether it's recognition or translation, then computer vision, driverless cars, and now medical imaging is also witnessing its use. So the question is, what is fueling this explosive growth? Well, there is, in medical imaging context, you can see that one thing that is helping is the image quality has greatly increased. So in 1997, the mammogram quality was like this. So it's hard to see what is the texture of the tissue inside the breast. It's a projection image. Whereas jump to 2016, you have much better quality. Next is what we call as PACS. So hospitals use something called a picture archival and communication system, where all the images are stored in a central server. So we have a huge collection of such images, and that also helps. And next, third ingredient in this explosive growth is high performance computing hardware, namely the GPU. So NVIDIA's stock value really shot up, not only because of gaming, but also because of deep learning and the NN renaissance. And finally, all these led to great advances in neural networks. So this is the inception network. So you can build a complicated, very deep architectures now. So now I will focus only on supervised type of deep learning because deep learning has become such a vast area. It's impossible to give you an insight into everything there. So I'll look at the supervised one. So how does this differ from machine learning? Well, here you once again start with image data and annotation or ground truth, and you have a deep neural network here, and you train it. And at the end of the training stage, we have what is called a model. And because the network has so much depth, it has many layers, and each layer has some parameters to be tuned. So you have millions of parameters that have to be tuned. So which means the training phase is very, very critical. And you need lots of data to get all the parameters tuned properly. Once you do that, you take the model and you send unseen image data, and it will give you the label for that image. So it could be that I am doing a task of, is this image normal or diseased? And that is a binary label. So the label will be normal, not normal. So in the deployment phase, the model is taken, data is given, and out comes the label. So if you look at this entire pipeline, I have an end-to-end solution, and the training phase adjusts all these millions of parameters. So as far as I'm concerned, I'm putting in something and getting out my label. So that's why we call it end-to-end. So I just do training with lots of data, and once the training is over, I get my task to be solved, such as label. So this requires, as I already mentioned, lots of data because of too many parameters. And if I have to go through training so much data, then I also need high performance computing. So let us look at key medical image analysis problem, which have been addressed using deep learning. So the first problem I would like to introduce is classification. As many of you might know, classification means given an image, assigning a label to it. So this is an example. So let's say I give a chest X-ray. These are all various diseases or various identification of what could be present in that image. So cardiomegaly means enlargement of the heart. Emphysema is basically some kind of pneumonia kind of disease. There is a mass in the lung, pneumothorax, then infiltration or pneumothorax, and so on and so forth. So you can see there are 8 different labels possible. In addition to normal, then it becomes 9 labels for any given X-ray. So this is a multi-class classification problem where the image is going in and you're training the neural network to give one of 9 labels to the image. So that is the image classification problem. And deep learning is most successful in the classification dimension. The second of particular interest to medical imaging is segmentation. Now here I am giving label at the image level, whereas segmentation is where I'm giving a label at the pixel or voxel level. Now why do I say voxel? Because I already told you that the image could be a 3D volume and not just a 2D like an X-ray. So you want to assign a label to each voxel. That it could be binary, so it belongs or does not belong to a structure. So you say 0 or 1, 0 means it doesn't belong to a structure, 1 means it belongs to a structure. Now what is this structure? Well, let us go back to the original example. So there is a fetus head I'm trying to discover from the image, and I label each pixel here as 0 or 1. 1 means it belongs to the fetus head. And once I do that, then I can find the boundary of that and then measure the circumference and so on and so forth. That is one class. Now, what about multi-class? We can do that also. So if I go back to my earlier example, namely mammogram, you can classify each pixel, because mammogram is 2D now, each pixel as having belonging to the mass class or a microcalcification class or a normal class. So this is a 3-class problem. So here we are showing the green box is a ground truth, and this colored region is basically the segmented mass. And you can see some here. It is too tiny, and that is the microcalcification region. So these are 2 key problems that have been addressed by deep learning so far. What sort of approaches do we use, even using deep learning? Now, medical domain has tons of data. That's what we all think. That's because there are so many hospitals, and every time you go to the hospital, they take images. But the problem is they're not curated, as in each image acquisition is done under a different setting. And also there are no labels or anything, so there's no annotation. And because medical images are of a person, a human being, there are privacy issues. So you must have all heard about data privacy. Now here, this data is medical image. So there's definitely a concern that somebody's data is being used for purposes it is not meant to. It was meant only for doctors to provide diagnosis, but if companies start using data to create products to sell, then that is a commercial purpose, which is not intended for. So there are a lot of laws prohibiting usage of medical data without patient's consent. So it is difficult to get data. So if you have difficulty in getting the data, so what do? Well, we can look at that problem later, but initially let me assume there is data. So what do? Transfer learning was initially popular. So we have deep learning done initially in computer vision kind of tasks where millions of data is available, and networks like VGG, ResNet, GoogleNet, all these networks are there, and they have been trained on these millions of images. So why not leverage such networks which are pre-trained and do a transfer learning? Transfer learning means you retrain it and change only the final layers, the weight of the final layers. Okay, you keep all the initial layer weights same as before. You change only the final layers. And the other method is you take the same VGG inception kind of network, but instead of changing the weights of only the final layers, you can retrain the entire network with medical data. That is also an approach one can use. And this thinking is, well, even if I have thrown away the pre-trained weights, the network is a good network and it's supposed to learn on general vision tasks. It has done very well. So if I retrain it with medical data, it should do well. That is the thinking. And that is the third method. There are also, you take VGG and make some variants of that. You make small modifications. Modification could be in the network architecture, modification could be in the loss function, and so on. So that means you start from something known, something that is known to work well, and make some changes so it performs well on the task that you are interested in. So that is the other approach. And finally comes the approach where good research labs and on difficult problems, they will design their own custom network. So you can see, if you want to do deep learning as a new student, you should start with transfer learning because this is the easiest thing to do. Next, you can try retraining or make small improvements. Finally, if you've mastered all this and have understood what works, what doesn't work, how the network is performing, then you design your own custom network. So this is the order in which I would recommend any beginner should do deep learning with medical images. So now let's look at a standard network in medical imaging. So in medical image analysis, there was a network called the UNet, which was proposed in 2015 for handling 2D images. And then it was extended to handle 3D images also just a year later. Let us look at this network and understand how it works. So the name UNet comes because of the shape of the network. And you can see I can draw an imaginary line in the middle. So the left of the line is basically the image is getting contracted here. And so you derived feature maps at every stage, at every blocks. There are 4 blocks, 1, 2, 3, 4. And this number indicates the size of the feature map. So you can see the feature map is increasing, whereas the image size is decreasing. So this starts with 64, and by the time it gets there, it's 512. Whereas here it is 572 by 572 image. And by the time it comes here, it is 68 square. So it is actually the image size is increasing, but I'm extracting more richer and richer features because I'm doing the job of an encoder. Now, there is also a counterpart to the encoder, which is the decoder. And here we basically start with this and we keep upsampling and going back to the original size. And then you have a final layer, which is basically, since I'm solving a segmentation task, I can do a binary classification. So it will be a final layer, which is converting this map into a binary label. And so this is basically doing an expansion. Now these lines are showing basically that I take the image here and copy and crop and add to it. So this thin line shows that I'm actually adding this. So these we call as skip connections. And so these are what we call as max pool connections and so on. So there are lots of jargon in deep learning. If you delve into it, you will learn. And so this is nothing but a CNN. You must have heard of it, convolutional neural network, because at each stage, each layer is actually doing convolutions. And the size of the filter that you're using is determined by you. So this is what we mean by parameters and so on. How many layers should you have? What size filters you should have? All these things are decided by you. So let's look at why I call this a standard network. It is extremely popular. So across organs, whether it is brain or abdomen or liver, it is used to do image analysis. So brain in general in medical imaging is the most studied organ. So you have maximum number of papers devoted. This is a paper that came out in 2020 looking at how many papers are published in a particular year. So this is 60 on brain alone. And eye is another popular one, and pathology is another one. So these are in the half, but still a decent number. Now, if you look in terms of modalities that I talked about, the UNet is popular across modalities also. So not only organs, but modalities also. You can see MR, of course, is maximum because brain means naturally MR, and CT, that is the next one. And I showed you a retinal fundus image, the color image. So that is another popular one. And X-ray chest, here also deep learning using UNet has been used for a variety of tasks. It could be classification, it could be segmentation, whatever it is, they will use a UNet. Now, if you think they use the same UNet, you're wrong. What did I say? They always try and do variations, because that is what research is all about. If you take a standard network and just apply it to the problem, it might not work. So what do you need to do to make it work well on a particular task is the job of the research. So what are the key variants? The first is to introduce the notion of attention. So in deep learning, introducing attention means there is a particular technique to make the network focus on specific structures of interest. Now, otherwise, if you think back, you are basically feeding data and you're getting a decision. So how do you know that the network is learning something meaningful? And if I have a chest X-ray, how do you make it learn to focus on the lungs, and so on and so forth. So that is attention variant. There's a second variant called the inception variant of UNet. So this is an attention UNet, this is an inception UNet. So in inception UNet, they take into account that your image could have structures of multiple sizes and shapes. So to make it work well, you want multiple size filters if it is a convolutional, because it is a CNN after all. So you want not fixed size filters, but multiple size filters in each layer, okay? And so that is the inception UNet. The third one would be residual UNet. The residual UNet is basically a deeper version with the residual skip connection. And these two together will control the vanishing gradients. It's a major problem in the any artificial neural network. Finally, there is a variant called the dense variant. So each block, there is 4 of them in the encoder section and 4 in the decoder section. Each one is a dense block, which means each layer receives connection from all the previous and so on. So why do we need this? Because they found that if you want to improve segmentation accuracy, especially in medical images where tissue variation is so subtle, if you want to get good segmentation, discriminating between these tissues, you need dense blocks. So these are the variants of UNet that have been tried. In my group, we tried a variant of our own. We call it the MNet. We published this in 2017, about 5 years ago. So the problem we looked at is how to segment deep structures in the brain. So we took MR, which is 3D. So we built a 3D to 2D converter. So basically for every slice, we take 50 slices around it, 25 before and 25 after, and combine it into one 2D slice, and then pass it to this network. Now, what changes have we made? The UNet, as before, has all these skip connections, but we also introduced skip connections here. That is because we found that feature learning is better and a smoother information propagation is smoother when you do skip connection at this level. Then we introduced 2 legs, one left leg and one right leg. The left leg basically takes the original image and adds it to the values to the next block and so on. So across each of these 4 blocks, I am actually taking the original intensity value and passing it on. So that helps. And finally, the right leg basically gets direct back propagation from the output and contributes to the final segmentation, which is happening here. So this MNet we used, This is the ground truth. I'm showing you one slice of the brain, MRI. And these are 6 structures in each of the half of the brain. We have 2 hemispheres. So 6 in one half and 6 in the other. So a total of 12 structures. And these are all labeled. And you can see the structures are of various shape and size. Okay. And they are colored differently to distinguish them from each other. So now that you understand that you can use standard networks, do variants and so on, let's move to the task of how do you build a computer-aided diagnosis system using deep learning. So in computer-aided diagnosis, or in our domain, we just call it CAD, we basically are interested in detecting from images diseases. So it could be breast, lung, skin, colon, cancer. So cancer of the breast, lung, skin, or colon. That is, these are, if you look at the literature, you will find lots of papers using DL trying to build a CAD system. Another class which is very, very popular, and my own group has worked on it a lot, is diabetic retinopathy and glaucoma detection from fundus images. So this is optical images. Here, it's, skin would be optical, this is X-ray, this would be MR, and this would be mammogram. Similarly, there are CAD systems which are being built for chest disease as well. Given a chest X-ray, can you do this? Or given a chest CT, can you classify it as COVID or non-COVID, and so on and so forth. So you have CAD system for so many diseases, and all built with images as input. How do you solve this? That's because these are also posed as image classification problems. So given an image, the CAD system that you build processes the images and gives a decision on whether it is belonging to a normal class or a disease class. Sometimes the disease class can be early, advanced, and so on, but it is still a classification problem. Now, even though it's a classification problem, it will require pixel level classification, which we call as segmentation. Sometimes we take multiple images, as I showed you in the case of brain tumor. So which means I need to do a spatial alignment across images, then fusion of information, and finally some quantification. So if my output is supposed to be early versus advanced, I need to do some quantification to decide that whether it is advanced or not. So all these are possible in a CAD system. So now let's look at how CAD systems are built. Well, the cost of CAD is basically with lots of data. So if you have lots of data, so in the old machine learning, which is this red graph, you have basically a certain plateauing of performance after some amount of data. So you keep increasing the data, the performance does not increase. So it is a saturation. Whereas in deep learning, which is the blue graph, you will see that the more data you use to train the system, the performance keep increasing. And that is the cost you pay for deep learning. That performance is linked to the size of the data with which you train. And if you see this in terms of how do you get this data, typically now big research labs in corporate research labs, they are the ones who can buy the data. And so industry giants have systems which perform at very high levels. Like Google has networks, whether in speech area or vision area, which perform extremely well. Speech, translation, everything. They are also trying to enter the medical domain. Now, small and medium companies like not giants, but they still perform here. So I would say academia performs somewhere here, maybe below them, because we cannot afford to get so much data. So this is one side of the story of the deep learning based CAD building. So academia could even be at the same level of this. I would say more optimistically somewhere here. Now, the second aspect about deep learning is there is a difference between the myth. So people think deep learning means lots of coding. But based on the previous slide, you should understand that deep learning depends on data so much. The training data means I need image plus annotation. So in the entire project that you do, most of it goes in getting training data. So if you are a startup company and you are thinking I'll hire a whole lot of engineers, make them do lots of coding and I will get a crack system, you're wrong. The experience shows that you actually need to invest a lot of money, not on human resources, but in buying data, getting training data. And then the next big chunk of investment has to be in experimenting, and coding is actually much smaller than even experimenting. So it should go this way. So you put in a lot of investment in getting training data, get the engineers to code, and then you get a whole lot of people to do lots of experiments. That is what deep learning for CAD system building requires. So a lot of startup companies have come up now in Hyderabad as well as Bangalore. They hire our graduates. They go to a lot of colleges and hire graduates. They offer internships and so on. They're all in this business, trying to get data, code, experiment, develop products. Now, talking of data, as I said, data is available in plenty in hospitals. So if you can work with them, that will be great. But unfortunately, as I said, it's not curated and it's restricted for distribution. Now, next thing I need is annotation, which is labels. So it could be local marking like this. So this is annotation done by 3 or 4 doctors. Why do you need that? When you have things which are not so clear, you need to take a consensus opinion of multiple doctors. Now, we Indians are known to even visit multiple hospitals to take second opinion, third opinion. So when you train a system to come up with a good decision, why not do the same? Get multiple experts to mark. So that is one way to think about it. And this is very, very difficult because this is in 2D. We did this work with the hospital and we had to get the doctors to come to IIIT to sit and do the marking. Otherwise, sitting in the hospital, they were constantly getting pulled out to go see a patient, and hospital doesn't want you to spend time doing this rather than seeing a patient. Now, if you go to CT, this is lung CT, and you are trying to do lung nodule. So the expert is marking the nodule with a circle, which is a tool that you develop. And because it's 3D, you have to examine each slice. So typically for the lung, you might have 100 to 120 slices covering the whole lung region. So in which case, to mark one image or one patient's image volume, you are actually asking the expert to go through 100 to 120 slices. It's extremely laborious, and that's why such markings are difficult to source. The DL solutions, you would think, are abundantly available because you look at conference publications or journal publications, there are so many papers. Each year, hundreds of papers are being published. So you would think actually the world is in a good place. DL is solving lots of problems. However, the reality is so few of them have been translated to clinical use, meaning so few of those solutions go beyond a paper, become robust solutions that doctors can use in the clinic. So this is a major concern in the medical imaging domain now. That is because we have, once again, a limitation in how you train and so on and so forth. So when you look at the data source, currently at the college level and institutional level, academic institution level, we rely heavily on public data. So this is freely accessible. So most conferences run some challenge or the other. So you just Google and say grand challenge, and you will see pages and pages of tasks, which are basically different medical image analysis challenges. BRATS is for the brain, this is for pathology, this is an Indian challenge that was run for diabetic retinopathy from the fundus image and so on and so forth. So typically an Indian student relies on this source. Take public data and build a system. And public data actually has become really more and more available. When I started in this area 15 years ago, there's hardly any. Whereas now in the last 5 years, it has really grown. And this is a good side of the story. There are also private data sources. So there are lots of public, research papers which say that they collected their own data and they will not give access to others. So if you want to benchmark your method, your model against another method, then there are two ways to do it. One is implement their method, which is difficult because in the deep learning era, you need to know what weights they use and this and that. So re-implementing their network is very difficult. So the second alternative is to test it on the same data set that they did. But if they use a private data set, what do? It's very difficult. So this is accessible only with permission. And there are two modes here. You can transfer the data to the lab for research. So you sign an agreement and hospital allows you to transfer the data. Another one is something I want to share with you, which is the most recent development in deep learning, and that is called federated learning. So how does federated learning work? Well, there are many forms. I will show you two methods. So this is federated model development. So this is published by a group in Hong Kong. So they basically developed a model which was sitting in central server. How did they develop? They worked with 3 different hospitals. And so the data went from each of the hospital, trained the model, and the weights came back, and so on and so forth. Test. So each site had basically here 7 cases, here 65 cases. So each hospital will share what they want. So here only 7 were shared, here 65 and 3 and so on. So you basically do an internal validation also. That's why there are 2 arrows. One is the training and the other one is a validation or the testing on some of the things. But when you have only 7 cases, it's very difficult to build a robust model. Whereas these 2 maybe, this would be better. So once you have developed a model, you want to validate on a completely different site, because that's when you get a really good final solution. So for that, what they did, they went to mainland China and Germany. So whereas these are all in Hong Kong, they went to mainland China and Germany. So there is an external validation they did by sending the model to 3 places in mainland China and 1 place in Germany. Now, when I say send, there are different ways of sending. The model is sent, tested on the images. So image never comes to the central server. and then the weights are sent back and so on. So this is one type of federated learning. Another type is where there is a central data server and there are 3 institutions. So each of them contributes some data to the data center, and there is an initial model which is sent to the data center, and it is trained, and out comes the final model. Now this means basically these 3 institutions should agree to share it with a central data center. Not all hospitals will agree. So that is why federated learning is still a developing area. Lots of people are trying lots of things, a very interesting area to watch out. Now, as I said, very few CAD solutions are being translated. So let me give you 2 options. So there is a DL model, image goes in, decision comes out, and the same image is given to a clinician, and the clinician also gives you a decision with some explanation also. Now you ask yourself, which one would you choose for your family member? So let's say it is your sister and something is wrong, so they took an image, and you have these 2 options. I am pretty sure, even though we are all enthusiastic about this one, we will go with this one for 2 reasons. One is, this is a clinician, it's a human being, and I can talk to this person, ask lots of questions. But even without that, they give explanation for their decision. They'll say, look, in this image, it's like this, and that's why we are diagnosing this. Whereas currently, most DL model will only give a decision. It won't say why that decision. This is a major problem behind why CAD systems developed in the research labs are not going to the clinic. So this is the problem, which is also a major area of research now, which is called explainability and interpretability of DL systems. So if you want a black box, if you build a black box, then it is not going to be used in a clinic, because we are dealing with human beings and everybody wants to know why a decision was made. And that is why this is another major area of research. So finally, I will share with you our own work in this area. So I just had a student who graduated in doing this work. And this is what we call as an explainable COVID detection. So during COVID, there was a lot of data publicly accessible. And so there are tons of papers which have come out. But if you look at how many have actually gone into the clinic, hardly any. So we looked at the problem and said, how do we make it explainable? Okay, so let me explain to you what I mean by explainable. Now, if you take the existing COVID detection methods, you will see that they will give you a heat map, or the GradCam attributions, we call it, as this. Now, these boxes are basically ground truth provided by the trained radiologist. They say they took the decision because these regions don't look normal. Whereas the heat map, red means the network found something is really wrong there, and blue means everything is normal, and so on. So let's understand what's going on. First of all, there's hardly any overlap, very little overlap, right? So the radiologist says this entire region is bad. Here there is a reasonable agreement, whereas it's not. But that is really not the main thing. If you look at the chest X-ray, the lungs are here. Okay, whereas it is giving some bad regions outside the lungs, even here. So here, so these are not even in lungs. What the network considered as reason to take a decision. And similarly here, it is very bad here. So it is saying outside the body region and something here. So basically, this is the problem with existing COVID detection methods. Our idea is to use attention, which I mentioned earlier, but at multiple scales to make the network focus on the lung region. So I won't take you, so this looks complicated, but it's not. So it's only a workflow. So we start with the chest X-ray and we do a lung segmentation. So we get a lung mask. So we multiply these two to extract the lung region. Okay, this is the original X-ray. This is the mask. I multiply, I get the lung region. Then I send it to a stage 1 system, which basically classifies this as normal or not normal. Normal means it's a healthy chest X-ray. If it is not normal, it could be pneumonia due to some other reason or COVID. So there is a second system which will separate it into ordinary pneumonia versus COVID. Now, why do we want this separation? Because COVID, as you know, is highly infectious. Okay, that's why we have quarantine rules, we have lockdown and all that. Whereas pneumonia is not. Pneumonia is something you get when you get drenched in the rain and get sick. Okay, there are other types also, but they're not infectious like this. So that is why we have a 3-class classification, but done in a hierarchical manner. So this is the workflow. So how do we do this? Well, we have something called our own custom architecture called MARL architecture. So the this is the architecture. I won't take you through the whole thing because it's quite complex. And so we take it through all this. And I want to show you the performance. So we basically work with a data set which is public, which has 8,000, nearly 9,000 normal images, 6,000 non-COVID pneumonia cases, and nearly 5,000 COVID pneumonia cases. And these are all X-ray images. And we used an 80-10-10 split. That means 80% of them were used in each class was used for training, 10% in each class was used for validation, and 10 for testing. And we did benchmarking with 2 other methods and a well-known architecture called COVIDNet. So when you look at our own network, which is the MARL network, we did basically cross-validation, both holdout method as well as 5-fold cross-validation method. And we can see that our method in a holdout mode performs the best, both in terms of F1 score and accuracy. And that's because if I go back, basically we are doing multi-scale attention, and that is coming from here. So there is an attention map here, and this is the multi-scale attention that we implement. And where is the explainability? Well, these boxes are the ground truth, and the heat map shows what our network actually found to be most critical part of the lung for the decision. And you can see that there is a good agreement between the heat map. The red region always lies within the box, okay? And so if you see this is a COVIDNet, and you can see that this found basically the bad region to be outside the box, whereas ours is always inside the box, okay? And so this is one way to convince. You give you give a decision, and then you show this heat map as an explanation, and then the doctor will say, yeah, I agree with this, and maybe I will use it, okay? Now, we also looked at the regional attribution for normal versus pneumonia by fitting bounding boxes to the attributes and how well they overlap with the ground truth. And for COVIDNet, the attribution accuracy was only 63%, whereas ours was 75%. And in terms of classification accuracy, they are the same. So this is the big difference. So the explanation basically is very good with our network, whereas with the existing network, performance is good, but hardly any explanation. In terms of F1 score also, they are on par. So this is a classic example where the CAD system performance is good, but the additional edge we are providing is the explanation. So I will now conclude this presentation with a few remarks. Medical images are very diverse because they use a wide variety of excitation sources. So they use advances in physics and use different kinds of sensors and so on and so forth to do the measurements and so on. So they are quite diverse. And because they're diverse, they can capture both structure and the function of the body. And to do any computing or analysis, you need a little bit of interest in interdisciplinary work, meaning you need to understand that if you're dealing with pneumonia, it is of the lung and not just anywhere in the body, and so on and so forth. That is some common sense stuff, but there can be more advanced understanding also. So working closely with an expert is important because after all, end users are in the medical domain. Now, we also saw that deep learning is a current paradigm, which is dominantly used for analysis. And deep learning is a little constrained, especially supervised methods for medical because annotated data availability is restricted. But then new techniques are being explored, such as federated learning and so on, that can help overcome these constraints. And DL solutions for CAD have potential for translation, provided they are explainable and interpretable. I hope you got a good overview of medical domain and how deep learning is at play in the medical domain. If there are any questions, I would be happy to take it. Are there any questions?
Yeah, hello, ma'am.
Yes.
Thank you, ma'am, for a very good insight I received. The concept of explainable is very really, it is a really means need of the explainability, because that is the limitation of nowadays deep learning models. Ma'am, can you suggest some data augmentation methods that we can use for medical? Means for medical data, it will. Like for other domains, we can use the other methods when in case where we have data set limited, but in
Yeah.
medical data, the
Right.
augmentation can be used. If so,
Yeah, I did not touch that because that's going to very low levels of. Yes, you are right in saying that the data augmentation methods that are used in computer vision may or may not be appropriate for medical domain. Now, if you look at the typical data augmentation is basically rotation, translation, and some contrast change and so on, right? That's what they do, the standard.
yes,
In medical domain, I think it is important to also figure out what is it. So you want to, so what people have tried is they do cropping, crop the image at a different levels, and crop it such that the region of interest or structure of interest is still in view, and so on. So in other words, so what does cropping do? You basically take a big image and you cut out smaller part of the image, right? That's what cropping does. Now, if you crop randomly, then you are basically not paying attention to whether the region that the network should be focusing on is still there or not. So rather than random cropping, intelligent cropping is important. So that is another, that is a major augmentation method people have tried and it works. And now if you look at rotation and so on, the level of rotation, sometimes they even do flip. Flip is basically reflection. And in the medical domain, depending on what you're dealing with, there is certain symmetry. So for instance, the brain has two hemispheres. So if you flip, you're basically flipping left and right. So you're really not adding too much. So even in retina, if you look at the optic disc, if you flip, you will get the same thing, slightly different, that's all. So all these things, that's what I meant by you need to understand the discipline in which you're working to see what will work and what doesn't. So why do we do augmentation? Augmentation is in order for the network to see new data or to see variations in the data. And if you keep that in mind, then you would do appropriate things. So the crop is one example.
Yes, ma'am. Thank you.
Okay. Any other question? So you're all students of what stage? What are you people studying? I have no idea. So for some of you, this might have been completely new. For some of you, partly new. So I don't know. Is Dr. Padma there? No? Okay. So if you have no questions, we will end the meeting. Feel free to email me. You can look up IEEE website, and my email address is available on my webpage. Please write to me and feel free to contact me. Otherwise, thanks for listening, and I hope you learned something today. Okay. Bye-bye.
Thank you.
Yeah. Okay.
That is okay. I will not come. I will ended it.
Yeah, YouTube లో
You have to go and start that. Understood now? Understood, Padi? Start. Or
Can you share this link also?
that is better.
Is there any admission permission for this, or people can join?
Only college, I think.
Oh, then అక్క మీకు
YouTube also there, but previously